All right, let's talk about one of the biggest, most fundamental rules in the entire universe. Seriously, it's a principle that dictates everything from how stars burn to how your phone charges. But this isn't just some dry fact from a textbook. Oh no. This rule was forged in the fire of a scientific war that lasted for over 100 years. Let's get into it. You've heard this a million times, right? The law of conservation of energy. It seems so simple, so obvious to us now. But what you're looking at here is basically the final sentence of a peace treaty that ended a massive scientific battle. So, how in the world did we land on such a profound idea? Well, it wasn't some eureka moment. It was a brutal, hard-won victory. It was pieced together through decades of fierce arguments, clever experiments, and a puzzle that stumped some of the most brilliant minds on the planet for a century. So, let's start at the beginning of the fight. Okay, so our story kicks off way back in the 17th century, and it starts with a huge showdown between two of the heaviest intellectual hitters of the time. The main question was this: when things are moving, bumping, and crashing into each other, what is the one thing that's actually being conserved? What's the true measure of force? The whole fight really boiled down to this. In one corner, you have René Descartes and his followers. He argued that the universe has a fixed amount of quantity of motion, which he said was just mass times speed. Simple enough. But in the other corner, you had Gottfried Wilhelm Leibniz. He said, no, the real thing that's conserved is what I call vis viva, or living force. And that, he argued, was mass times speed squared. And believe me, this was way more than just a math argument. It was a deep, philosophical clash about how the universe actually works. Let's just quickly put this on a timeline so you can see how it all played out. It really gets started with Galileo in 1638. He's the one who first spots a connection between how far something falls and the square of its speed. That's a huge clue right there. A few years later, Descartes comes out with his quantity of motion idea. But then, Christian Huygens, who was an absolute genius, shows that in perfect collisions, mass times speed squared is what stays the same. And finally, in 1686, Leibniz gives it a catchy name, vis viva, and basically lights the fuse on this huge controversy. For the next 100 years, a full century, the scientific community was totally stuck. And you want to know why? Because both sides seemed to be right, just in different situations. Newton's famous laws, for example, they really backed up the idea of momentum conservation, which is a lot like Descartes' original idea. But you couldn't deny Huygens' experiments with pendulums and colliding balls. They perfectly backed up Leibniz's living force. You see the problem? They were both seeing a piece of the truth, but a huge chunk of the puzzle was still missing. So the thing that finally broke this century-long deadlock didn't come from a new theory or a complicated equation. Nope, it came from an experiment. The story now jumps forward to the 1840s, and to a guy named James Prescott Joule, a brewer who happened to be a brilliant physicist. He had a hunch that the missing piece wasn't another kind of force, but something they'd all been ignoring: heat. So Joule builds this absolutely ingenious device. The idea behind it was actually pretty simple. He had a falling weight tied to a string, and that string would turn a little paddle wheel that was sitting inside a sealed container of water. He just wanted to see where all the mechanical work from that falling weight was actually going. And this is how it worked. It's beautiful. So the weight starts up high, full of potential energy. As it falls, that potential energy turns into the kinetic energy of the spinning paddle. Then, and here's the magic, the paddle churns the water, and friction makes the water get warmer. That was it. The big breakthrough. The mechanical energy from the weight wasn't just disappearing into thin air. It was being transformed, joule for joule, directly into heat. And just like that, with Joule's discovery, the old vis viva debate was over. It was finally settled. Turns out, Descartes and Leibniz were both kind of right. They just couldn't see the whole picture. Mechanical energy and heat weren't separate things. They were just two different forms of a single universal quantity. They were both just energy. And now, at long last, scientists could finally write down the rule. And here it is, in all its glory, the first law of thermodynamics. The total energy of an isolated system is constant. You can change it from potential to kinetic, from mechanical to thermal, from chemical to electrical. You can change its form all you want. But the total amount? That never, ever changes. Now, this one law has some really powerful implications. It's basically the ultimate accounting principle of the universe. What goes in must come out. And it means you absolutely cannot get something for nothing. That old dream of building a perpetual motion machine that just creates energy out of nowhere? This law is precisely why that's impossible. It's the universe's ultimate no free lunch rule. Okay, so to actually use this law in the real world, like if you want to design an engine or figure out a chemical reaction, you have to be really specific about what you're looking at. You have to define your system and where its boundaries are. And the first big question you have to ask is, are we dealing with an open system or a closed one? And the difference is actually really simple. Just picture a pot of boiling water on the stove with no lid. That's an open system, right? Both energy, the heat, and mass, the steam, are escaping out into the kitchen. Now, what happens if you put a really tight lid on it? Well, now it's a closed system. Energy can still get out as heat through the sides of the pot, but the mass, all that water and steam, is trapped inside. The first law works for both. You just have to account for things a little differently. So after this incredible journey of more than 200 years, we finally have our law. But so what? Why does this actually matter to any of us today? Well, honestly, it's almost impossible to overstate how important this is. Think about it. This one idea that started as a philosophical fight between Leibniz and Descartes and was finally proven with a paddle and a bucket of water, it is the absolute bedrock of modern science and engineering. Every engine in every car, every power plant, every chemical process, they are all designed around this fundamental law. It even explains how energy flows through entire ecosystems, all the way from the sun to plants and then to animals. It's everything. So the first law gives us this incredible, unbreakable rule for how the universe operates. The cosmic bank account of energy is fixed. You can't make deposits and you can't make withdrawals. But it leaves us with one last, gigantic question. If energy can't be created, then where did all the energy we have now come from in the first place? And that, my friends, is a story for another time.